try it. I think one of the easy ones is right here. Right, the 0 is nice. Plugging in a 0, the population is 500 when you plug in a 0 for t. Well, if you plug in a 0 for t, that's a 0. This whole thing's a big 0, and guess what? C is 500. That's awesome. This next piece of information should help me find k, I guess. When you plug in a 1, the population is 600. Okay, the population is 600. The k I don't know. Oh, I'm plugging in a 1. That's easy. 1 to the 3 halves is a 1. There is a 2/3 there. And then plus c, which is 500. And so I can find k. I'm going to subtract, it's going to be 100, k times 2/3, multiply by 3 halves, and you get 150. So k is 150. So now you have an actual population equation. You had to integrate, and then you had to use some what's called initial conditions. You had to integrate, and you had to use some data, some conditions, an initial condition. But that helped you find your population equation, which is so this k, what's this k? 150? But it's 150 times 2/3. If you don't mind, that's 100. I mean, it's 150 times 2/3. And then this is a plus 500. Cool. Right, we got a population equation. And now I can answer the question. Let's plug in a 7 and see what the population is. Right. Cool. Let's plug in a 7 and see what the population is. Everybody knows the square root of 7 cubed is, I'm kidding. Everybody knows the square root of 7 cubed is 24.61. Am I right? Could have got lucky. Everybody knows the square root of 7 cubed is 18.73.
Yeah, I got 18.5. 18.5.
Dude, you give me long enough, I'll nail it. All right, times 100 plus 500. If you don't mind, just tell me. 23. 52. 0.03. Don't ignore that 0.03 of a bacteria.
K is 150, isn't it?
Well, it is, but then what do we do? When we plugged it in here, it was multiplied by the 2/3.
Yeah.
Right. So the K was a 150. Multiplied by the 2/3, change that. Right. So is that the number? Is that the answer? Bacteria.
Yes.
Thank you. All right, listen. If I want to stay in 5.1, what comes next is some, good old. There's some vertical motion. They call it vertical motion. There's also some horizontal motion. They call that rectilinear motion. But the big concept is, if you have position and take a derivative, you get velocity. If you take a derivative of velocity, you get acceleration. Or if you start with acceleration and integrate, you get velocity. And integrate velocity, you get position. I mean, so that's it. But then you fight through the physics, the words and the physics to answer these questions. So you ought to try that and ask me for help. I assigned a lot of these. I could try helping you with one, or I kind of feel like moving to the next section, to tell you the truth. What do you got? You got anything pressing on your mind? Okay, good. Let's move on. Listen, I'll get back to that. That's important. Acceleration, velocity, position. I'll get back to some of those. I want to move to 5.2, and the truth is I really don't want to do 5.2. I did 5.2 the other day. I added up rectangles. You guys should add up some rectangles. I'm kind of tired of it. If you make me, I guess I'll have to do one. But in 5.2, let me just show you. What did I assign? I assigned 25. You're supposed to do 4 rectangles. 28, you got to do 8 rectangles. Maybe I'd skip that one if I was you. 29, you got to do 4 rectangles. 33, 34, 35, they drew the rectangles for you. You got to do those 4 or 5 or 6 rectangles, whatever they give you. On the next page, there's some midpoint rectangles, the middle rectangles. So that's it. There's about 12, 13 problems, something like that, adding up a few rectangles. So you ought to try it. And I'll help you. I'm moving on though. I'm moving to 5.3, where we learned, where I had earlier here, I had that the big idea in 5.3 was, again, I wrote this up here, that if you're integrating from A to B, what that is visually is it's the area under a curve from A to B. It's this area under the curve called f of x. So now they got a lot of cool ways of getting at this concept. I mean, like I said, they make you... I want to do some of this homework. Yeah, here's 20. Look at 20. 20 gives you a picture of a function. It's 4 over x squared plus 2. They give you this picture. It's a beautiful picture. It's a beautiful function. It looks like this. And they shaded this. They gave you this function. They gave you this picture. They shaded this. And their question is, please set up a definite integral that yields the area of this region. By the way, the word region is a correct word. This is a flat region of area. And can you just set up? They don't even want you to do it because, again, they haven't taught you how to do these definite integrals. But can you set up a definite integral? Who would you be integrating?
4 over x squared plus 2.
That's right. I mean, whatever the picture is, that's the function you're integrating. Some students get confused. They think they gotta, no. Whatever's in the picture, that's the function you're integrating. Because, by the way, if you remember the idea of the rectangles, maybe I skipped over those rectangles today, but those rectangles had a height. And this is the function was the height. The function is the y value. So it's the height of my rectangles, multiplied by the widths of my rectangles. I mean, when you set up an integral, maybe you're not thinking of rectangles. I'm trying to make you a little bit, but maybe you don't have to. But behind the scenes, there's a bunch of damn little thin rectangles there, and this is their height, and these are their little widths. And there's millions of them. There's millions of them. So, I mean, when we're doing an integral, there's an infinite number of rectangles. Anyway, what would be a good left bound and a good right bound? And by the way, these bounds are x values. So what are they?
-1, 1.
Thank you. I mean, is that easy or what? The picture gives you this, right? And we're done because they didn't say, they haven't taught me how to integrate this yet. And the truth is, I don't know how to do this. Is kind of a tough one anyway. Anyway. I mean, yeah. I don't want to, yeah. Sorry. 5.3 ain't about, let's finish this. 5.3 is about, can you go from the picture to the integral or from the integral to the picture? And that's all it is, kind of. Let's do one more here. Look at this one. 24. What's funny about 24 is they gave me this, a function of y minus 2 squared. This is 24 in 5.3. And they gave me this picture. They were nice. They gave me a picture. 24, yeah. This is 2. This hits here at 4. And they shaded this. And so, when I presented this topic to you of that a definite integral is area, I keep referring to this. I say this definite integral is this area. This is what this section's all about. Now they just threw a little kink at me here. What they did was they gave me a function of y. By the way, if it's a function of y, then this is x. This is, right, this f of x is y, right? This is y equals, well, this is x equals. And so I didn't tell you this, but the truth is, you can do these integrals. If they're a function of y, then you're doing them with respect to y. And then I'm going to use some different letters, C to D here. And the truth is, it's kind of like you're turning your head sideways. You know, I call this the area under the curve down to the x-axis. Well, now, if it's given as a function of y, it's the area under the curve down to the y-axis. So if you had some function of y, some x equals a function of y, and you're going from some C to some D, you're finding this area. That area to the x-axis. I mean, to the y-axis. Everything changed. Everything's in y's. The bounds are in y's. The function's in y's. You're integrating with respect to y. The picture, it's like you turned your head sideways, and this is your new x-axis, is your old y-axis. You're integrating from C to D, from a lower number to a higher number. So now that I told you that, maybe we can set this one up. I want to set up an integral, but I think this time I'm going to set it up with respect to y. I think I'm going to put my function in here, which is already in y's. And I think I'll put the bounds on here. What bounds would you put on here?
0 to 2.
Thank you very much. Right. The error would be to say 0 to 4. Most all these problems are in x's, and so you get in the habit of doing it in x's, but here's one that's in y's. So your bounds are 0 to 2. You're right. You're exactly right. You guys okay? Any questions? I'm trying to help you with some homework because it's easy. You know, here's one. I'm just making this one up, but it looks like one of your homework problems. Now I'm going to go backwards. Here's an integral. Sorry. 16 minus x squared is what that's supposed to be there, dx. So the question is, don't do this integral. You can't do this integral. By the way, you can't do this integral. Maybe someday if you take Cal 2, somewhere up in Chapter 8, we learn how to do this, actually learn how to do this. But right now you can't do it. But that ain't the point. The point is, the question is, can you draw a picture of what it represents? And if we think of it as area under a curve from -4 to 4, I need to draw a picture of this curve. So here's a curve here. Now, if someone says draw a picture of a curve, what do you do? I mean, this is my function. This is my f of x is what are you going to go do? What are you going to do? Pick up your graphing calculator? I would, I guess, unless I know what it is. I do know what it is, but you might not. So if you're going to go sketch this, you pick up your graphing calculator and you type this in. Maybe you set a good window to where you're working from -4 to 4, but you get a beautiful picture of this. You can see what this is. This happens to be, maybe I should wait till you do it. But if you type this in and look at it, it's a semicircle. It sure is. It's a semicircle, by the way, of radius 4. So it goes from -4 to 4, which is exactly what they wanted. From -4 to 4, under this function, this is a semicircle. So what did I do? They gave me this and asked me to draw a picture of what it represents. I picked up my calculator and typed this in my graphing calculator, I guess, so I could get a graph of this semicircle from -4 to 4. And I'm done. That's all they wanted. there are some problems in 5.3 where they'll say this. Listen to this. Because again, they haven't taught you how to do this. So you can't do this and get the answer. But what you could do is look at that and say, well, it's a semicircle. They say, use geometry to get the answer. Now I don't think they did this anyway. I think this question was, here's an integral, please sketch the region of area. Good job. But there's some other questions that say, use geometry to tell me the damn answer. And what would you say? Well, it's a circle. Well, but wait a minute. The area of a circle is pi r squared. That's what you would say, but it's half a circle. So maybe it's pi r squared over 2. And what's the radius of the circle? Can you tell?
Radius is 4.
What's the radius?
4.
Thank you. Okay, so here we go. Pi r squared over 2. This is using geometry to help me get the answer to this is 16 over 2. This is 8 pi. I mean, that's this area, 8 pi. But that's from geometry and knowing the shape and knowing. If you did the calculus, the answer would be 8 pi. But I can't teach you this calculus until chapter 8. Can't. This is hard to integrate. But it's a semicircle, radius 4. Geometry helps me get the answer. So guess what? I think you can do that when it's circles, semicircles, rectangles, triangles, maybe even trapezoids. But not when it's this.
Right.
There ain't no geometry to help you with this. I mean, you gotta do the integral. You gotta do the integral. So, but in 5.3, haven't taught you how to do the integral. So they do resort to this geometry. They have some questions about using geometry. Hey, look at this. Watch this. Watch this problem. So what did I just do to you? Oh, I gave you an integral and said represent it, please, with a picture. So we did. All right. Here's a funny one. Watch this one. Let's represent this with a picture. You ready? I want to represent this with a picture. So, so I'm going to draw a picture. Okay, so I'm going to draw a graph. I got an x-axis and a y-axis, and what am I drawing here? Who do I draw? What do I draw? Do I draw? The function that's in there is the function you draw. Some people get confused. They think, oh, you got to integrate and then draw that. No. The function the integrand is the function in the picture. So I should draw a sine function. Okay, you guys know what a sine function looks like? Kind of starts at 0, kind of does this. That's a little drastic. It's got a height of 1, -1. It's got an amplitude of, let's see, when it goes all the way over here, let's see, this is pi. When it completes one cycle, that's its period, 2 pi, right, you guys?
Yep.
So here's a beautiful picture of a sine function, y equals sine x. All right, wait a minute, I'm supposed to shade some area. I should shade the area from 0 to 2 pi, right?
Right.
So what area would that be? Oh, between the function and the x-axis. That's sort of how these things are defined. Between the function and the x-axis. That's what I've been doing. So this one's funny because it dips below the x-axis. So I think the area would be this. Do you agree? Mm-hmm. Okay. So if the question was, draw a picture of there, okay, you're done, I guess. You did it. But when I want to point something out to you, this is kind of weird, but I'm going to point this out. Let's actually do this one, okay? Even though we're not supposed to know how to do it. I'm going to do it. So now I'm sort of taking you up into 5.4, just for a second. I did this last week. I did 1. I'm about to do another 1 here. Let's see. So now I'm trying to integrate sine. Integrate sine. How the hell do you? It's the antiderivative of sine. I should know it. Because I should know my damn derivative. So I should know my antiderivatives, I guess. I get confused. Listen, I got to go like this. I do like a little 2-step dance. You ready? The derivative of sine is cosine. So the integral of cosine is sine.
Right.
Did you hear that? It wasn't much of a dance, I know. I'm just bear with. All right. So hang on. What did I just say? The derivative of sine is cosine. So if you're trying to integrate cosine, you get back to sine. All right. That's not what I'm doing. Okay. So hold on. Let's go with the other dance. If I'm taking the derivative of cosine, I get negative sine. So if you're integrating a sine, you get negative cosine. Yeah. All right, cool. So the answer is negative cosine x. I evaluate it from 0 to 2 pi. This is 5.4, and what that means is you plug the 2 pi in, negative cosine of 2 pi minus negative cosine of 0. There's a negative sign on the function, but when you plug these in, you do subtract them. So this negative sign is part of the fundamental theorem of calculus is plug the 2 pi in, plug the 0 in, and subtract them. So what is the cosine of 2 pi? It's a 1. It's a 1, but it's a negative sign, so it's a negative 1. What's the cosine of 0? It's a 1. With 2 negative signs in front of it, it's a plus 1. So what's the answer to this? 0. So see that shaded area? It's 0. Wait, does that bother you? I mean, right, area ain't supposed to be 0. I mean, you don't shade a bunch of area and call it 0. Right? I don't go paint this wall and say, oh, how much paint's on there? Oh, 0. But I did here. I just did here. And here's the explanation. An integral treats area under the x-axis as negative. And again, you might try to argue, area ain't negative. God damn it. Area is, oh, excuse me. Area. You might try to argue and say area ain't negative. You're kind of right. Area is a measured quantity that should be positive. So here's what I'm telling you this. An integral treats area under the x-axis as a negative quantity. So what it did was it added up that area, it added up that area, and added them together, and it was 0. Whatever area it got there, this is the same area, but it's negative. The answer to this is 0. And how do you justify that if you think this is area? You justify it by saying, oh, area above the x-axis is positive, area below the x-axis is negative, and they canceled each other out, and I got a net value of 0. Are you with me? I'm not trying to confuse you, but an integral treats area under the x-axis as negative. And that's kind of important, a little concept. So what if you really wanted this shaded area? Okay, hang on. What if you really wanted this shaded area? I tried to get it, maybe, and I got 0. So how could I adapt my work? What could I do to really get this shaded area? What could I do?
Just do 1 to pi.
Just go from 0 to pi,
Right.
and maybe, if I really wanted all this shaded area, then maybe double it. Maybe double the answer? Yeah, let's go from 0 to pi. We'll get that area and we'll double it. If I really wanted all that area, the truth is I might just want, but let's try it. Let's try this. So how do you integrate a sine? Cosine? No, negative cosine. Negative cosine. From 0 to pi, you plug your pi in. That's negative cosine pi minus negative cosine 0. Let's see this. This is a negative 1, actually, you guys. Cosine of pi is negative 1. With that negative sign, it's a positive 1. That is a positive 1. This answer is 2. Now, wait a minute. I forgot to double it, but that's okay. This answer is 2. From 0 to pi, that's a 2. So if I wanted to double it, I'd multiply by 2, and I'd call all that area 4. See, this is me using my brain, because I know if I just integrate from 0 to 2 pi, then I know what an integral does. An integral treats area below the x-axis as negative. So it's just going to cancel itself out. So if I got to overcome what an integral does, I have to be a human that's more knowledgeable than this stuff. And I have to figure out what to do. Oh, I'll do half of it and double the answer. That's 2 and that's 2. Yeah. I don't know. There's some good problems in here. Let me think here. There's also these properties of these integrals. Let me go over a couple properties before I leave here. So I'm in 5.3, and here's a funny property. Watch this. If you ever do an integral from a to a, you know what the answer is? A. No. This is so weird. Go over here to this picture. You're integrating a function from a to b. I mean, we know what it is. But if you're going from a to a, that means you're going from a to a. These are infinitesimally thin lines. How much area do you get from a to a?
1, 2, 3.
Nothing. You get nothing. There's no area under the function from a to a. Are you following me? From a to a, you haven't gone anywhere. I mean, there is a line there, but and I know it looks thick with my marker, but there's no thickness to this line. There is no area from a to a. This is nothing. By the way, though, if you think ahead toward the fundamental theorem of calculus, what would you do? You'd integrate it. You'd evaluate it from a to a. You plug your a in, you plug your other a in, and you subtract them. Well, you get 0 if you think about the. But that's 5.4 kind of. All right, so there's a property. Here's a funny property. If you go from a to b, it's actually the exact negative of going from b to a. Which is weird. We like to set up our bounds from left to right. We like to set up our bounds from A to B. I mean, that's what this is, you know. That's what this picture is. From A to B, f of x dx. But if for some reason you got one going from B to A, it's going to give you a negative area. It's going to give you, I mean, whatever this is, you get this area. Maybe it's 6. If you did it from B to A, it would be negative 6. That's what this says. It's the exact negative of this. Oh, by the way, if you remember the fundamental theorem of calculus, you'd be subtracting your things backwards. One of them, when you plug your numbers in and subtract them, you'd be subtracting them backwards, which is the exact negative of something. Here's another one. Watch this. If you're trying to integrate from A to B of a function, and C lives in between there, watch, you know what you could do? You could go from A to C plus from C to B. Now, I know I'm being a little abstract. Let me show you a picture here. What I'm saying is, you're trying to integrate from A to B, but there's a number C that lives somewhere in between. And you're trying to integrate this function. So, you know, if you're going from A to B, you know, that's the whole area from A to B. That's the whole area from A to B. But what you could do is go from A to C. That's part of it. And then go from C to B. That's the other part of it. And add them together. Are you following me? It's very logical. You can go from A to C, and you can go from C to B. Get 2 different areas, and add them together to get the total area from A to B. So these are properties, and then your book has clever ways of asking you some questions. I've assigned some problems in 5.3. I haven't really got to them today yet. But they've got clever ways of asking you questions to think about these properties. They're very easy logical properties, but deciphering how they ask their questions might be a bit of a challenge. There's not, in 5.3, there's not a lot of hard work. It's just, how does the integral represent itself as area, kind of. But there's not a lot of calculations you have to do. Let's see, was there some other funny properties of integrals? Let me think here. Yeah, you can pull that constant out. That's true too. Actually, I better quit, I guess. All right, so I'm quitting today. Thank you for listening. I'll see you Wednesday.